Yes. Thank you very much for the invitation to speak here. It's been a real honor and a pleasure working with Jose and Colin over the last several months. I'm very sorry not to be there. Rimini, of course, is a wonderful place, of which I have many fond memories. So I hope there's another occasion before too long. We were chatting just before the beginning of this talk, and Michael Harris asked whether there have been any conclusions. But as we know, asking questions that have answers is really no fun. So this is the title. The question in the title is another one of these questions with no answer. But nonetheless, I thought I would try to give a very naive one. Naive meaning it's not really an answer. And then Jose and Colin will follow with much more sophisticated commentary. In fact, the original title of those sections were sophisticated commentary, but they forced me to take out that adjective because they're too modest. But I will launch in with my naive answer to the question I posed. Somehow, I was focusing more on this question of why is arithmetic geometry, and being somewhat stubborn about not really thinking about the transformation of numbers because that's so hard for me. So hopefully my collaborators will comment on that more. So here is an approach to the naive answer, which is, again, very well known to most of the people in the room, but I will try to be quick. So there's something called the algebraic geometry that I think most people have heard about. This is where you study the geometry of zero sets of polynomial equations. So in a way, whatever kind of geometry you're interested in, these tend to be important examples looking at zero sets of polynomials because somehow they're very easy to describe. Right? And just as a matter of notation, I'll denote the equation itself by x too, because it's supposed to be a geometric object. And x bracket a will be the solutions to this equation in some ring. And when people talk about algebraic geometry proper, the tendency is to focus on the complex solution. I find this also a little bit curious because, after all, naturally people may have been interested in real algebraic sets, but these days that's regarded as a much more specialized subject. And if somebody works on algebraic geometry, they usually mean they're working on this complex solutions of equations like this. How historically that came about, maybe some of you know, I don't really know. So here are some of the obvious examples, just to make sure that I have some equations on the slide for us to be referring to for concreteness every now and then to fix ideas. So most of the time, I don't think about these higher variable equations, and my own expertise tends to be limited to two variables because it gets very hard when you increase the number of variables or the dimension. What about the arithmetic geometry? So that's a very brief overview of algebraic geometry, which I hope is more or less familiar to everybody. What happens in arithmetic geometry is we're concerned with numbers, rings of numbers, in other words, number systems, or you can add and subtract and multiply, that are rather small. So one way of thinking about the kind of rings we're interested in, the number systems we're interested in, these are those things that have a kind of intrinsic discreteness, like the ones I have example I put on the slide, Z, or Z with just allowing the square root of -1, or Z and throwing in the square root of -1 and square root of -2, and so on. So this bracket means that you allow those numbers, then look at all numbers where you apply the arithmetic, the algebraic operations on those numbers, addition, multiplication, and subtraction. And then you get a ring, a number system. And these kind of number systems we view as having a kind of intrinsic discreteness. And a slightly more abstract way to say it is that arithmetic geometry is concerned with finitely generated rings. That's exactly the way I described this just now, right? So Z, you can think of as being just generated by 0 and 1 after applying the operations, right? And then you get a few more numbers thrown in all these other examples. So arithmetic geometry is about finitely generated rings. And also, in terms of the solution sets, I was already started out saying something about solution sets. We also tend to be interested in solution sets in small rings, finitely generated rings themselves. Right? And from that point of view, just the focus, I mean, there are other aspects of arithmetic geometry as well, but just focusing on solution sets of this, it's sometimes called Diophantine geometry, and is viewed as a branch of number theory. Solutions to integer solutions to equations, polynomial equations type of questions. So just to give you a few snapshots of why people do this from the point of view of solving equations. Again, this is probably known to many people, but if you're interested in the equation, I should have written it down. X squared plus y squared equals 1, for example, you can find rational solutions by using this geometric method, right? Which it's very hard to trace the historic origin of. But anyways, what you do is you find one solution here, -1, 0, and you then consider all the rational slope lines that go through that point, and then it intersects the circle, x squared plus y squared equals 0, one other point, and if you solve for it, you get solutions like this, rational number solutions like this one down here, which is for t equals 10. You can generate rational solutions to the rather tricky equation x squared plus y squared equals 1 easily by using this geometric method. This is the case of conics, and then of course there's also the very well-known case of elliptic curves, where there's a cubic equation in two variables. Now this is supposed to be, sometimes people say this is historically the first elliptic curve, although we never believe first anything, claims of the sort that something is the first of anything. But anyways, this appeared in Diophantes's book as a challenge problem, and if you want to generate rational solutions to this equation, you do something similar to what we did for the case of conics, except in this case, when you have 2 points, you can generate a third rational point. So that's the idea for generating rational solutions to this equation. For example, you can start out with a trivial solution like this and keep applying this operation and getting more and more complicated solutions. So these are the kind of solutions that you would never have found unless you were looking at this from a geometric point of view, at least as far as I know. Maybe somebody has great algebraic intuition enabling them to do this without the geometry, but it's hard to believe. Now, let's return to the general question of arithmetic geometry. As we said, in arithmetic geometry, we are looking at defining equations that are inside a finitely generated ring, or intrinsically discrete ring. But one thing you have to be slightly careful about is that this actually comprises all of algebraic geometry, if you phrase it in this way, because if you take any complex polynomial, it has only finitely many coefficients. So to define it, you only need a finitely generated number system. So you could, if you just focus on this defining equations, algebraic geometry and arithmetic geometry are no different. So instead, arithmetic geometry focuses not on defining equations, but on rings of functions. So here's the typical example. So here you're actually interested in functions on this elliptic curve y squared equals x cubed minus 1. Right? So you view them as two variable polynomials where two of them are identified if they vanish on the curve, right? So of course, this is one way of thinking about algebraic functions on an elliptic curve. But if you consider the polynomials as being complex polynomials, then that's algebraic geometry. If you would consider them as having integer coefficients, then that would be arithmetic geometry. In other words, what we're saying is that it's not just the defining equation that has to be somehow defined by a small ring, but it's the whole ring of functions that we tend to focus on and insist that be finite. So this out of the algebraic geometry of the 1950s and 60s, Grothendieck and so on, there was this method for taking any commutative ring with unit and viewing it as the ring of functions on a space. That space is sometimes called the spectrum of that ring. So for those of you who have some familiarity with physics, this is actually the same notion as what they have in physics, except the only difference is that the values of the so-called pure states, it can have varying values. It doesn't take values into complex numbers or something. Anyways, there's this construction of a geometry associated with a commutative ring, which we aren't going to cover right now. But in any case, this is a way of viewing any commutative ring as a ring of functions. And from that point of view, arithmetic geometry studies schemes like this, spectra of rings, where the ring itself is finitely generated, like the example we just saw. And So you see, somehow the focus of finiteness now has shifted just from the coefficients of the defining equation to the ring of functions itself when you're doing arithmetic geometry. A general arithmetic scheme, by the way, is something that you get by taking finite union of spectra of finitely generated ring. That's the subject of arithmetic geometry. That's all there is to it. In scheme theory, you have this phenomenon that if you have a ring homomorphism, you can view this as pulling back functions via a map between spaces. So there's a map of scheme going in the opposite direction, spectra going in the opposite direction. So this also is of great interest in arithmetic geometry. So for example, just to give you a flavor of why, if you take a ring like ZXY, polynomial ring in two variables, and consider the maps from the scheme spec Z to spec A, right? Then that turns out to be just Z squared, just pairs of integers. The reason for that is very easy. It's because to get, remember, a map like this is supposed to be a ring homomorphism in the other direction, but to get such a ring homomorphism, all you have to do is assign some number to X and some number to Y. In other words, a ring homomorphism case is just a pair of integers. So in turn, a map from spec Z to spec A is a pair of integers as well. Similarly, if you take a more complicated ring, like taking a quotient, like if you quotient out by the equation for the elliptic curve, for example, then to consider a ring homomorphism from this quotient ring to Z, you can just compose it with the quotient map from ZXY to this thing. So this is a surjective map. So of course, ring homomorphisms here are determined by this composed ring homomorphism. So you can see that the ring homomorphisms will be subset of Z squared, right? But it's also not easy, so that's what I wrote here, right? But it's also not hard to see that, remember, we described the ring homomorphisms here as just being given by assigning integer values to X and Y. When does that factor through this quotient ring? Is exactly when this pair of integers actually satisfies this equation, right? So that's that. So in other words, the integer solutions to equations of this sort are naturally bijective with maps of schemes like this. So the study of solutions to equations becomes a study of mapping spaces. This is all part of the yoga of arithmetic geometry. And even though it seems like it requires a lot of abstract machinery to set this all up, you might even say a majority of the important results in Diophantine geometry have somehow used this perspective over the last 50 years or so. Now, let me give with that background, let me give my naive answer to why arithmetic geometry is geometry and pass the baton over to my sophisticated colleagues. Why geometry? Well, so one thing is that if you look at this construction of a spectrum, there's this funny thing that if you consider an ideal inside the ring, that determines a subscheme, because that ideal, using that ideal, we can construct this quotient ring. But because I should have written this, A maps to the quotient ring, you get a map from spec of that quotient ring to spec of A. And so this is the way you construct subschemes of spec of A. These correspond to ideals. And this correspondence has lots of natural properties. So for example, by the way, you should think about this Z of I here, the spec of the A mod I, as being the subscheme where I vanishes, corresponding to the vanishing locus of the functions in I, of the elements in I. So then it's from that point of view, it's easy to see that if you have an ideal that contains another idea, if it's bigger, then you're putting more conditions. So its zero set, the subscheme corresponding to I, will be contained inside the subscheme corresponding to J. So this kind of natural inclusions can be read off from the relation between ideals. And similarly with intersections, you can see that if two subschemes will intersect non-trivially, we'll have non-trivial intersection exactly when the sum of the ideals is not the whole ring. So there are lots of properties like this. There are also more sophisticated things like computing intersection multiplicities with homological algebra of these rings and ideals. So the point is that this spec A and its subscheme seems to constitute exactly the kind of model for a geometry. So that's, I think, the very quick reason or naive reason, or the easiest reason that comes to my mind anyway. So why one should think of arithmetic geometry as geometry. So I realized a slight irony when I was preparing this lecture, because I usually don't like this kind of axiomatic approach to geometry. But here, I guess I'm arguing that the structure of a scheme and its subscheme is pretty much like what you see in axiomatic approaches to geometry. It's a model for some version of such an axiomatic theory. I'll also briefly remark that when you consider these kind of arithmetic schemes, there are also construction of things like vector bundles, differential forms, tangent spaces, and so forth. They can also, in other words, lots of usual geometric construction just carry over, except for the fact that we have sort of exotic objects that are not so easy to interpret using usual geometry, like spectrum of Z or spectrum of a finite field. So the second, slightly better answer, which I think Colin likes very much for why arithmetic geometry, is because we have these Grothendieck topology, which are very powerful tools and surprisingly rich in structure. Now, some people like to distinguish geometry and topology. I'm not particularly fond of that distinction. It's all somehow study of shape. So this discussion is included in the discussion of why geometry. So in other words, given a scheme, there's this idea that you can regard certain maps from Y to X, some other schemes to X, as being like open subsets, right? Even if it's not a subset. And then you set up a notion of topology using special classes of such maps. And that's the idea of Grothendieck topology. And then you have the theory of open covers and so on. But once you have an open cover, you have some combinatorics of this kind of coverings, intersections, and intersections of intersections, and so on. So there's a certain combinatorics of coverings, which pretty much behaves like the combinatorics of a checked nerve of a topological space. It's also very similar to dividing a space up into simplices, right? So using this, you can generalize usual notions of topology. We get a very, very rich theory corresponding to this kind of topology, and it leads to lots of number theoretic consequences. For example, the Weil conjectures and also various cases of the Langlands correspondence. These all tend to use different notions. Well, mostly they are topology, but sometimes you go somewhere beyond it. This is really, of course, one of the great triumphs and surprises of arithmetic geometry of the last 60 years or so. I was also going to say a little bit about the Weil conjectures, but I think I've used up my 30, and now I think I've used up slightly over than 15 minutes, I think. So, Jose and Colin, what do you think? Should I just pass over to you now?
So I'm going to talk about conceptual change in the idea of whole number. The oldest idea of number is probably counting numbers, 1, 2, 3. Another would define numbers by Panoraxons. I'm not going into those, but I bring them up to say there's lots of conceptions of number. They're not just one of natural number. I'm not talking about rationals or reals or anything like that. I'm talking about different conceptions of natural numbers and integers. I'm not going to distinguish natural from integer much. I'm going to illustrate one or two, you can decide, newer algebraic ideas of the standard integers in number theory. I'm curious how this looks to analytic number theorists, because this is very algebraic, so presumably it looks different to them. But one aspect began with André Weil's 1927 Arithmetic on Algebraic Varieties. Carl Ludwig Siegel immediately picked this term up. To him, it looked terrific. The other is Emmy Netter's working class field theory, which Olga Towsky-Todd said she had trouble understanding because her own training was in number theory, the kind that involves numbers. André Weil expressed his viewpoint in Latin. This is the viewpoint I want to get to. Nihil est in arithmetico, quod non prius flaret in algebraico. Everything in arithmetic first comes from algebra. And he really, really means this. He really means the truths of number theory begin as truths of algebra. And then you can sort of show them off by turning them into number theory. Algebraic results like Hilbert's theorem 90 or Weil's decomposition theorem, which is pretty technical, you don't run into it everywhere. These are not technical tools serving arithmetic. For Weil, the algebra truly comes first. Facts of arithmetic are specializations in more basic algebra. And I will have to thank the organizers at this point because I had such a ball learning this. I did not know this until I started writing for this. This was so little like arithmetic that no one in France could read his dissertation. The day of his defense, he's driving around town trying to get somebody to agree to write up the report. He's got the top professors in math in France on his side, but they don't want to write a report on this dissertation because they can't read it. No one in the world could read it except Siegel in Germany and Louis Mordell in England. Number theory was fairly out of fashion, and this number theory was so novel, it was just, people could not read it. And I will say, a beautiful source on this, Jean-Pierre Serre's biographical memoir on Weil. It's just such a right match. Serre was the only person who could have written this take on André Weil. Weil's central method in his dissertation and much of his career was to focus on primality and common divisors as the key feature of integers, not induction. Look, I do plenty of proof theory of Peano arithmetic. I love induction. But for Weil, that's not a key property. Of course, he needs to use it sometimes, but it's not the key. The key is primality and common divisors, which, as I recalled while I was writing this, is how Euclid treats numbers in the elements. And again, this is the usual integers, but also algebraic integers and algebraic number fields, and polynomials regarded as entire functions, as the integers in function fields. There were a lot of these analogies available. Weil, as a teenager, started toward his dissertation, he got everything started very early, with what he called a virtually obvious remark already hidden in Fermat's work. He discovered this on vacation in the French Alps. I don't know any pictures from his family, but you can get beautiful postcards of the town they lived in. This became the basis for Weil's decomposition theorem. My calculations showed me Fermat's methods, as well as his successors, all rest on one virtually obvious remark. And again, he's not kidding. He's not saying this occurs somewhere. He's claiming, whether rightly or not, but certainly this is his conception, and he's André Weil, that they all rest on this obvious remark. If pxy and qxy are homogeneous polynomials, algebraically prime to each other with integer coefficients, and xy are integers prime to each other, then the values pxy and qxy are almost prime to each other. Their GCD admits a finite number of possible values. I mean, it would be great if algebraically prime polynomials applied to relatively prime numbers always gave relatively prime values. They don't. But there's a bound on how far from that they can be, and more precisely, if homogeneous integer polynomials, pxy and qxy, have no non-unit common factor in rational polynomials in two variables, then there's an integer d such that for any coprime integers a and b, every common divisor of the values PAB and QAB divides D. That's what he means by a bound. There's one fixed integer that bounds all the common divisors of any pair of values for relatively prime arguments. And I can tell you on good authority that a lot of very good number theorists, they don't find this a very attractive statement at first. But he's a 17-year-old on vacation with his family, you know. And remember, for Weil, this is secondary. It's a simple arithmetic consequence of a deeper algebraic truth, specifically the Euclidean algorithm for one-variable polynomials over a field. This is the arithmetic show of Euclidean algorithm for one-variable polynomials over a field. Let me first give an example. Very familiar. I don't know when I first met this example, long before I had any information on the subject. Take x plus y, x minus y. For relatively prime numbers a, b, the values a plus b and a minus b could have a common factor of 2, or might not, but they cannot have any other common factor. The common factors are bounded at 2, which means, for example, if the product of these two polynomials, oh, no, here it is. If the product of these two polynomials is a square, then the values of the two must be a square up to a possible misplaced factor of 2. So this comes into arguments by descent all the time. It would be great if, whenever the product was a square, the individual numerical values were squares, and they almost are. They are up to a possible mismatch of a factor of 2. And the proof automatically works for polynomials over any algebraic number field. Oh, function, this is a persistent typo in this set of slides. It means number field, algebraic number field. It works automatically over any, very famously, We's dissertation solved problems that were given in terms of ordinary integers and rationals, problems that had become famous in terms of ordinary integers and rationals, but his solution automatically works in the relative case over any algebraic number field. And I'll sketch the virtually obvious proof. I'm nervous because okay, good. Suppose pxy and qxy, these are polynomials with no common non-constant factors in qxy. Then I can dehomogenize. I can divide through by y and get one variable polynomials that also have no common factors. This is high school algebra. Now, high school students wouldn't know the motive for doing this algebra, but they're able to do this algebra. And in that case, there are polynomials ux and vx such that the weighted sum is 1. That's Euclidean algorithm. In fact, you could do it for any greatest common divisor, but in this case, it's 1. Now, rehomogenize by y, multiply by an integer common denominator to m, and you get this equation. So for any integers a and b whatsoever, no primality here, every common factor of the values divides m b to the k. Similarly, for some integer n, it divides n a to the j, so it divides both mn b to the k and mn a to the j, and now, when a and b are co-prime, mn is a linear combination of those two. So the bound is the product mn. That's what makes it number theory. The substantial part was proving Euclidean algorithm, and that's not super hard either. But this is simply clearing denominators. That brings us to Evie Nutter. Her focus on number theory, her earliest work included number theory along with algebraic geometry as a motivation, but in the mid-20s she starts focusing on number theory, specifically the task of creating local class field theory as a basis for all class field theory. She uses her homomorphism and isomorphism theorems in non-commutative algebra. She treats Galois representations as modules, well as modules on the group rings of Galois groups. She's got a beautiful theory for modules over any ring, and she just uses that theory. She does not use specific numbers. Olgatowski-Todd was right about that. At least in her publications, there's no numbers. You don't see them. But she and her colleagues knew that the arithmetic was reflected in structural relations between the algebras. For example, Pythagorean triples are fully described by Hilbert's theorem 90. They are not normally explained to high school students in terms of Hilbert's theorem 90, but to number theorists they are, and I'm sure a lot of you are real familiar with this. But I'll still spell it out to show it's this general method. A Gaussian rational number has norm 1 if and only if it satisfies the dehomogenized Pythagorean equation. We're going to get the same solutions as Minhyong got by his geometric construction, but we're going to do it by Hilbert's theorem 90. By theorem 90, all those solutions have this form. They can all be written as a Gaussian integer over its conjugate. That is far from obvious. It It is an algebraic calculation, and I want to stress that I'm using algebra here in the sense we've been calling theory of equations. It's just algorithmic application of the formal properties of plus times, add, minus, and divide. It's really theory of equations. And again, the calculation to verify this, I could teach it to a smart 10th grader. I couldn't teach them why I'm doing it, but I could teach them to do it. Well, so you just simplify. So the solutions to equation 1, I got question marks which should say 1, have this form, and that's the one that Minhyong gave you because he stopped with rational solutions. And now simply clear denominators, and you get the integer solutions. Now, if you're concerned to only get relatively prime solutions, you would add some more conditions. But a historical question that genuinely interests me, in 1930, when Netter proved that, did her friends Paul Alexandrov and Heinz Hopf notice the algebraic analogy between her statement of Hilbert's theorem 90 and how she taught them to define the first cohomology group of a topological space? Looking at it from a modern point of view, it leaps off the page. You say, look, these are the same sequences you would have written if you were doing topology. I do not know, Netter says nothing about that. Her friends were more attuned to topology. I don't know if they knew that. But historical certainties, Hopf knew all about it by the late 40s because Netter's student McLean, along with topologist Eilenberg, had organized Netter's hypercomplex algebra into group cohomology. From there, Artin and Tate, following Hochschild and Nakayama at Princeton. Hochschild and Nakayama often don't get mentioned, but Artin and Tate mention them as having done this first. Specialized this into Galois cohomology as the basis of class field theory. Theorem 90, it becomes this very pretty equation, and all you need to know about this equation is how pretty it is. Be sure to consider it pretty. If you don't consider it pretty, you don't understand these people. That's a very sweet equation. Serre and Grothendieck made Galois cohomology into the étale cohomology of zero-dimensional schemes, which opened the way to étale cohomology of finite-dimensional schemes. And so that brings us to where Minhyong picked up. Thank you.
Okay, so it's been a pleasure to work with Colin and Minhyong. And so after their sophisticated presentations, let me say a few simple things, very simple things. So in a way, what I want to say is a footnote to Cavallés when he says that mathematics is a becoming. So all I want to comment is a little bit on how things appear in different lights when you consider them from a very abstract first principles perspective on the one hand, or when you consider them from the point of view of the historical development and you introduce the historical component. So I wanted to say something about that. And well, I can skip the first phrase. So I will focus mostly on the part on geometry. As you saw, Kim was talking about the geometry, Colin was talking about the evolution of number and conceptions of number. Now, the evolution of conceptions of space, of course, and of geometry is an extremely complicated subject because, for one thing, it covers all of human history. And things seemed very simple 200 years ago, but they don't seem so simple nowadays. So one thing I wanted to mention, just in passing, just to show this a little bit, is that until 1900, which is quite late, the word space is used mostly for physical space. So it immediately has a physical connotation, in which, of course, the space, this space around us, let's be naive, and it is unique and in fact supposed to be Euclidean. Jesper Lutzen has a recent paper in which he goes through examples in the 19th century to show this situation with the word space. So in 1900, people were just starting to get used to the word space, meaning something quite different, which is the current meaning in mathematics. Out of a large number of abstract structures. One can think, of course, of Hilbert's Grundlagen. One can think of Hausdorff characterizing topological space. He uses the word Raum there, so we see this changing in meaning. Many things could be said, of course. Now, with Hilbert, geometry becomes the study of spaces, where we mean by space structures that, of course, I would suggest, I may be wrong, of course, please correct me if I'm wrong, but I tend to think that at the time, early 20th century, people were thinking about the structures strongly reminiscent of the Euclidean space of traditional mathematics and classical physics. So there is this, you see the historical background all the time, or at least maybe it's my bias to see things this way. So if Riemann, by the way, introduced a new word precisely because Raum was physics, the physical space, so he needed a more abstract term to think more abstractly about these things. So he introduced the word manifold, as Tabea was reminding us this morning. And the manifold had to be continuous, let's say, in the concrete, intuitive meaning of the sense of this word. So the tendency is to think of things resembling one-dimensional real line, two-dimensional complex, and so on and so forth. So I'm just saying very well-known things. Sorry about that. By 1900, there is this plurality of geometries. Many people think that projective geometry is the broad picture, and within that you get many things. Of course, there was the issue of non-Euclidean geometries that Roy was telling us the other day. Now, I just want to mention two important lines of work at the time that were received very well, precisely because they brought some general scheme to place all of this variety of geometries, which is the Erlangen program type of approach, study of invariants under a group, on the one hand, and there is the differential geometry more or less along Riemann's lines, which was minority at the time, but anyway, there it was. Of course, 1900 geometry brings Poincaré to mind, and he was always emphasizing the group approach. Now, if for one moment we forget about history and we try to think about this in terms of very abstract first principles, perhaps the idea that geometry has to be of one of these kinds is too restrictive, or it may even seem like a cliche. I heard somebody say this. So, of course, from a more modern perspective, you can think of much more, in a much freer way about spaces and geometries. So, coming to the topic, to better understand the geometry in arithmetic geometry, it seems to me essential to consider the transformations undergone by notions of number and notions of space during the 20th century, and in this case, especially, of course, in the context of algebraic geometry. So I'm kind of repeating myself here. I should go quick. Maybe I can skip this. In the naive context of the 1900s, we have this heritage of classical analysis, geometry, and mathematical physics dominating, and this explains some of the focuses at the time. With the increasing abstraction and freedom brought by the development of structural mathematics, things have changed and moved away from there in many different ways. And this one can think, for instance, of Zariski reconstructing algebraic geometry, the Zariski topology, and how these things are interestingly different from the more traditional ideas. So here, I guess I was putting a few ideas that Colin suggested in our exchanges. The new topological ideas do not express intuitions of distance, straight lines, or real numbers that may belong to the more classical way of thinking, but they still capture spatial ideas or intuitions of continuity, covering, intersection, connection. Minhyong was mentioning these things. So we have that, which is interesting, and I think explains to some extent the situation. And in particular, I wanted to mention also that we have these hybrid structures that have become more and more common. And in particular, I find very interesting these hybrids that mediate between the discreteness of numbers and the continuity of classical spaces, which are particularly important in this setting. And I think probably I should be stopping. I can do it just by letting you with this phrase from Grothendieck. He is talking about toposes, but we can apply basically the same idea to the things that Minhyong was talking about. And the quotation is very nice. The countless other types of structures which until then had seemed irremediably anchored to the arithmetic world of discontinuous or discrete aggregates. So one thing that Grothendieck really enjoys is this hybrid mediators making possible this unification. And that's all I wanted to say. So thank you.
Reconstruction of algebraic geometry. Why it's a reconstruction and why it's not
I'm not the person to tell you the details, but there is this whole issue of the development of algebraic geometry, how Zariski had learned from the Italian school, the difficulties there were in terms of proofs and rigor and so on and so forth, with results of the Italian school in the early 20th century. And then there is this reconstruction employing algebraic, more modern algebraic methods and new ideas. So that's what I meant. So the new versions of algebraic geometry typically, correct me if I'm wrong, and there is people here who know much more. But things start importantly with Zariski, then come other people like Weil, employing all of the machinery of modern mathematical methods to reconstruct algebraic geometry. That's what I meant.
It's really a question that tries to understand how I can put together what Minhyong said and what you said, Colin. And this is an attempt to try to understand where you intersect in how you reflect upon, for Minhyong, the relationship between algebraic geometry and arithmetic geometry, and what you said about the relationship between algebra and arithmetic, for instance, for Weil. Could you try to guide me more on how you think the relationship between the two in these two parts of the talk?
They was immersed in everything that was going on in number theory at this time. He knew the work by Noether, Brouwer, and the others. He knew how an algebraic conception of number was really empowering class field theory by creating local class field theory. Given all of this, he wanted an algebraic, he called this Kroneker's idea. He wanted an algebraic geometry that would deal with integers, that wouldn't have to be over a field, let alone an algebraically closed field. This was not going to be easy. He saw how the Zariski topology could be a basis for doing this in his book, Foundations of Algebraic Geometry. But this book was very, very hard to learn. And it didn't look like it was going to produce an actual algebraic geometry over integers, because it really only worked over algebraically closed fields. So something more was needed. Serre introduced several ideas. He introduces structure sheaves as a geometrizing device. There's an algebraic idea of a structure sheaf over a space, which in the case of polynomial rings agrees with what would later become scheme theory. It was scheme theory using only polynomial rings. Grothendieck looks at this and says, there was no reason for that restriction. Serre has very well said, no one invented scheme theory. Everybody in Paris who was interested knew how you would do it over arbitrary rings if you wanted to, but what he says is, nobody except Grothendieck wanted to, because everybody thought if you didn't have a Noetherian condition or something like that, it would be too hard to work with and it wouldn't relate to anything. But of course, as Serre saw over the next couple of years, yeah, it really did. You can drop nearly everything about a geometric space. Drop the coordinates, drop the continuity, drop everything except the plus times divide algebra of polynomials. And you can give basic geometry. Now, there's a lot of theorems of classical geometry that you won't get there. You're going to need to restore special information. But you can get started really well without any more information than that. And this suited the Weil conjectures perfectly, because it was pretty clear that nothing like classical intuitions in topology would ever vindicate those conjectures. So here we have a radically alternative view that, as Serre says, anybody knew how to do if you wanted to, and as Serre also says, Grothendieck correctly saw, you do want to.
Maybe Minhyong wants to say something.
No, I don't think so. I think Colin said. No, I don't have much to add. Unless there's something specific about my contribution, Corinne, you wanted to ask about.
No, I just wanted to try to put the two together, and because the meaning of arithmetic and the meaning of algebra is fluctuating, but perhaps we can, no, that's okay, we can talk later. Okay.
Maybe I will say one thing. I think that the way I understood the connection between Colin's part and my part was that when you set up the scheme theory, the way I briefly alluded to, geometry and algebra are just the same thing in some sense. They're just dual to each other, right? And the difference between algebraic geometry and arithmetic geometry is only a question of what kind of algebra you're considering. And I think this is pretty much in line with what Colin was describing.
Yeah. The success of the Netter approach used all the same algebra you would want anyway. So Weil says, well, Serre and Grothendieck say, let's just use that algebra. We'll use it the whole way through.
By the way, Colin, maybe one thing that maybe because of my ignorance about history I wouldn't agree with is that I don't think he's dropping Noetherian conditions or things like that was really what the driving force. It was to my mind, it was more, do you get something really useful about thinking about things like spectrum of Z?
Yeah, in the larger picture, that is what worked. But right. The fact that you could prove a whole basic stratum with no assumptions except that it's a ring made the subject a lot more attractive. But yeah, the serious results start when you have Noetherian conditions and other things like that.
Well, but what I'm saying is that the very, very general framework, I'm still not sure that that's what makes the subject attractive. At least for me personally, what makes the subject attractive is being able to consider something like spec Z.
Yeah, well, that's if you want more substantial results. But you can't write chapter 1 of EGA without those conditions.
No, I understand, but I guess what I mean is that these great generalities isn't what most mathematicians find very attractive. I guess that's the point I'm trying to make.
Okay, so I have a sort of historical question for Jose, but for all of you somehow. So I just consider the notion of space because what I find interesting is between the end of the 19th century and the beginning of 20th, the pluralities came in first for geometries, then it came for structures. So it was common even in Pieri to say we have relations between structures, that's geometry. But very late, spaces arrived in plurals. So the question would be, when does space arrive in plural, and when do they stop talking about systems and structures, but still really space?
Well, as far as I know, the answer is spaces in the plural. This is 1900, more or less. And the structure is a late word to come. So, I mean, people will be talking about systems, will be talking about manifolds. Even Husserl, I was reading recently something of Husserl about manifolds, and so on and so forth. I don't know if you have.
I agree.
Yeah, not only Hilbert. Look at Hausdorff, for instance. He has very nice, there's some very interesting material having to do with his reflections about the space and time, wanting to modify the conceptions of space and time for science, but in order to do that using the mathematics of sets. And he has some papers in the 1905 or something like that, which is extremely modernist in the way he presents his views. And so from then on, I think, and of course, 1914, you have his elements of set theory, the Grundzüge, where you have topological space and so on and so forth.
You mean that Grothendieck topology is a topology in the same sense as classical topology, or is very different in the spirit and so on?
Well, here I will invoke some wonderful conversations I've had with Pierre Deligne. Formally, it's quite different. But in someone's hands like Deligne, not only does he immediately see it as the same as topology, he gets me to immediately see it as the same as topology. You can really think of it as if it was just a topology of open sets, although it is not at all.
The concept of sheaves, and then
Yeah.
it's something very different.
Well, but in that context, Grothendieck topologies work as well as point set topologies.
Maybe I could add a little bit to that answer. I think the whole point of Grothendieck topology is to set things up, develop the language necessary to see these things as the same. Once you set up the language correctly, you see that ordinary topologies, especially sheaves are an ordinary topology, and there's more general notions of sheaves are actually the same thing. And so Colin and Jose and I had a short discussion about this, is that oftentimes these kind of abstractions that Grothendieck seems to like is often about unifying many disparate looking concepts into one. It's not abstraction for its own sake. So I guess Colin had even a quote from Grothendieck where he mentions this himself, and that's what's going on in this question of Grothendieck topology as well. It really is the same, but at the cost of a little bit of abstraction.
Michael, it's your turn now.
Oh, thank you. I just have a couple of points to add. First of all, I've been wondering for some time whether the developments over the past years in particularly focused in Bonn and in Princeton represent a real break with the kind of around derived algebraic geometry and so on, and higher topos theory represent a break with Grothendieck's version of geometry, or whether it's in continuity or a natural extension. One point, because increasingly papers in this area start with long explanations of categories, and you get the impression that the only objects in geometry are the categories of sheaves on categories and so on. And in higher versions. And the second point is that all of these abstractions are motivated ultimately to the extent, or going back to Wei's proof of the Riemann hypothesis, by wanting to count things and developing methods that allow you to say that some construction that is that does not appear to preserve, as Colin said, the intuition of geometry, the classical intuition of geometry, nevertheless can be adapted so as to give you, at the end of the calculations, a number. For example, in intersection theory, the number of solutions of equations over finite fields, or the number of curves on a moduli space in physics. And so somehow the motivation for all of these developments in geometry is largely concealed. If the subject matter of geometry is the construction of six functor formalisms, as it seems to be increasingly, nevertheless, all the aim seems to be to get numbers at the end.
Well, even today, to a lot of people, the numbers seem to be concealed in class field theory. And these people are just wrong. The numbers are revealed by class field theory. Revealing the numbers was the point of all this all along, and it worked. But you do it by algebraic devices that don't look much like numbers. I've got friends who still think class field theory is just insane.
Okay.
Mike, I didn't quite hear. Did you have a question, or was there a comment?
Yeah, there was a question about whether there's a continuity, or whether this represents something really different, the derived algebraic geometry as a method, and higher category theory, and so on. In some sense, it was anticipated by Grothendieck, and even he scolded people periodically for not having created this. But it feels very different in some sense.
Actually, I would have viewed them as very much in continuity. I'm not an expert, of course, but if you take the idea, just to focus on part of your question, you should take derived algebraic geometry, right? What are you doing there? All you are doing is taking the ring of sheaf of, if you take the ring of functions itself and endow that with a topology. That's the idea of derived geometry to a large extent, right? Because you're considering simplicial rings of sheaves of functions. So it's just taking Grothendieck idea of sheaves of functions, and just endowing that itself with a topology. Now you have both topologies, topology on the underlying space and the topology on the rings. So to me, that feels very much in continuity with the old ideas.
Okay, so it's coffee time. So we thank Jose, Colin, and Minhyong again.
No, thank you.